Welcome to Exploratory Lesson 2. In this lesson, we're going to just go over the basics of how to calculate covariance and correlation, as well as this thing called R squared, and talk about those things. But as you learned in the lesson, we're also talking about if statements in this chapter. And those are really important to spreadsheets and to programming generally, because it's how you build a machine that is able to, really think something through. If statements direct it one way or another across a series of decisions that can be very complex and very complicated by the end. So, understanding the if statement is really at the core of being able to build a really functional spreadsheet that can do a lot. So, let's go over that. Here's this data that I have. This is real data of the actual global average temperature anomaly relative to this time period, and the CO2 in parts per million in the atmosphere of the Earth over time, as measured by scientists. And so this is kind of the data that gets looked at that points to climate change. That you can see, like in 1850, relative to the average temperature of the Earth between 1961 and 1990. In 1850, it was almost half a degree. I think this is in Celsius, colder than in that time period. And if we go to 2021 or even 2020 here, you can see it's almost a full degree Celsius hotter on average than it was in that time period. So this is sort of our climate change data. And I put this in here because this is a chapter about correlation and how correlation is not causation. So let's just do this first. Let's look at the correlation. Let's highlight columns B and C and insert in here a chart. And it's giving me a line chart that's not actually what I want. The chart that I want is a scatter plot. So on the chart editor here, if you had clicked the X, if you don't see this here, if you click on your chart and click your three dots, edit chart will bring up this chart editor. And then you click this chart type and scroll down to get the scatter plot, which is really what we want to take a look at here. And this is showing us this sort of relationship. It almost looks pretty flat here if you take a look at it. But we could adjust our axes if we want. We could have this minimum value be 200 and this maximum value, we could keep that at 450. Maybe even we want this at 250 to really show this slope on here. But of course, now I'm manipulating the axis of the data. Lots of people will tell you that's a big no-no, but really when you're presenting data, what you want to be able to do is, what you want your audience to be able to do is come to the correct conclusion. That's the key. So if keeping this, at a minimum of 0 makes it hard to come to the correct conclusion that there has been a change here, or that there is a correlation, then it is worthwhile to alter this axis to show that we can see that, over this very large range of values, there has been a lot of correlated movement from one to another. As the CO2 in parts per million has increased, so too has the average temperature of the Earth. That's what the data tells us. Now, of course, the point here is, in this chapter, that such a correlation is not causation. And in order to determine whether or not human activity has increased the density of CO2 in the atmosphere, and that in turn has increased the temperature, we need more scientific evidence. And of course, there is that. But I want to build to it. And we'll see this again at the end, where we really will be able to test against alternative hypotheses for why the Earth might have gotten warmer over this time period, and determine whether or not we really can conclude that it is human activity or not. Because that is a main part of the debate that has occurred. Lots of people who reject that human activity has caused climate change do so on the grounds of correlation is not causation. But of course, this has been looked at for many decades now, and there is quite a bit of evidence that you really ought to conclude that it is human activity. But we should be skeptical. That is, one of the key things to learn from this course is to be skeptical of this stuff. We live in an age where a lot of people will say, do your own research, or they'll claim to have done their own research and reached preposterous conclusions about things on which they have no expertise. We're living in a world where everybody thinks they know enough to find the truth. This class is actually about figuring out what you need to know in order to know the truth. How can we tell what is true and what is false? What does it actually mean to do your own research? And how is it possible to even reach a conclusion that A is causing B? That is what we are entering into over this course. So let's keep going with that. One of the things that often gets cited about this data is, nobody in 1850 was actually measuring the average temperature of the Earth. These are estimates that have been reached through alternative means, looking around at the environment and seeing, things that have been preserved from that time that would have been altered at different temperatures. But it's less reliable than the data that we have since like 1978, at which point there were satellites in space orbiting the Earth, whose purpose was to measure the temperature around the Earth. And so that data is a lot more reliable. So that's going to be our first if statement. I just want us to learn how to use these if statements. And so we're going to do that. So here in this column, we'll do if, and we just want to check the year. Is this year greater than or equal to 1978? Now, this is our logical expression that we're putting in here. This logical expression has to render as either true or false. And so when it looks at A2, it will see the value 1850. It will compare that now to the value of 1978 and check, is it greater or equal to that? And that will come back false in this case. But we want this formula, this function, to extend to the cells below. Eventually, we're going to get to 1990, and it's going to compare that to 1978, and we want that to come back true. So we need to give it instructions for both when it is true and when it is false. And you can see it's popping up, letting us know that this particular expression will render as false. If it is true, then I just want it to return the value 1. And if it is false, then I just want it to return the value 0. And that's just a nice, simple way of doing things here to figure out, is this year greater than or equal to 1978? 1 and 0, these are just indicators. 0 is just going to mean no. 1 is just going to mean yes. And so there we have it. It has properly identified 1975 is the last one to come back false, and 1978 is the first one to come back true, and so does every year after that. So that's what an if statement does. It just checks a logical statement, and then returns a value if that logical statement comes back true, and a different value if it comes back false. We also have ifs statements, multiple if statements kind of stacked together, where there's more than one thing that really could happen. So let's do this ifs. Ifs has us first put a condition and then a value. This value is going to be the value that it returns if the first condition is true. So what I want to do is check and see, is our observation falling within the years where this global average temperature anomaly is relative to? Is it between the years 1961 and 1990? So first, what I need to do is get something that's going to take us out of this if statement and return a value. So we're going to have to actually reverse the conditions here. We want to know if we're between 1961 and 1990. So I'm going to have it kick us out with a value if we're not between those numbers. So the first thing I'm going to do is check, is this year less than 1961? Because if it's less than 1961, then it's not in between 1961 and 1990. And so then the value I'm going to have it return, I'm just going to have it return false. And I'm just going to leave it like that, because false is just a Boolean value. And so you see that it is blue here, which means that the spreadsheet is able to read it as a particular value. And sometimes you want it to do that. Our second condition then is going to be, are you greater than 1990? So we're going to check, is A2 greater than 1990? And if that's the case, then we'll do false. That's our value. Now, here's a really tricky part. These Boolean values are read true or false, and so are these. This is actually a Boolean value, and you can see it's rendering as true in this case. And so because this is true, the function is going to return the value false. If this were false, then we wouldn't return that value. We would go to this condition and check it. If this comes back true, then we would return false. Otherwise, we continue on. And so now in our last condition here, we've sort of exhausted everything we need to know. So I want this condition to always clear out. I always want it to come back true. So in order for it to always come back true, I'm just going to put in true. And then the value for true will be true. This is kind of complicated, and it's worth taking a moment to really think through the logic of this and draw it out on a piece of paper as a diagram about what is going on with the function and how is it going to return certain values. But when I plug this in, you can see it does work. Starting in 1965, we start getting trues, and that goes to 1990, after which we get false. So you can see here this returning these proper values. Now, another thing I can do that I'm going to show you with true and false, if I highlight these values, I can insert here and I can insert checkboxes, and you'll see that when it's true, it is checked. This is just worth noting that checkboxes, they either are true or false. True means checked, false means not checked. And so that's very useful in Google Sheets to know that you can sort of check a box with a formula. So you can see we have in here a formula that is checking this box, and here a formula that's unchecking it. Okay, so now the easy part. Let's calculate the covariance using a formula. This one is a bit weird. So covariance here, covar, this is the population covariance. And that's kind of a problem for us. We're always going to want the sample covariance. And so instead of covar, you can't really use covar in this case. You have to use covariance.s. And then we're going to give it the data, column B and column C. And then it's going to calculate this covariance for us, 15.63. Covariance, sort of like variance, the magnitude doesn't have an interpretation. Really, here only has an interpretation if it's positive or negative. Because this value is positive, what I can say is when the global average temperature was above average, it usually is the case that CO2 in parts per million is also above average. And when one is below average, the other one tends to be below average. That's what a positive covariance tells us, is that they sort of move together. When one is up, so is the other. When one is down, so is the other. Correlation is how we get a sense of the magnitude, and this function is called correl. Correl will put in column B and column C, and it will return a value between -1 and +1. Correlation coefficients are always between -1 and +1. Here we get 0.97. And now we can see, in our graph, it was kind of hard to see that there was a strong correlation here, but indeed there is. The maximum correlation is +1 or -1. A negative correlation would mean they just move opposite of each other, and on the graph we would have data going in a downward slope direction. But this is a positive correlation, so the data is moving in a positive direction with each other. It's moving upwards as it goes along. And it's very strong. It's very close to 1. So this is a very strong positive correlation between global average temperature and CO2 in parts per million. There's another statistic called R squared. R squared, correlation, sometimes is referred to as Pearson's R coefficient. That R is the letter we often use to represent correlation. If we square that value, then we get this. And this is usually written as a percentage. So we get 94.15% if we square that value. And here's what that means. 94.15% of the differences in average temperature across the years. So 94.15% of the changes in temperature are explained by or correspond to the changes in CO2 in parts per million. So we cannot conclude causation here yet. We cannot say one is causing the other. But if CO2 in parts per million is causing global average temperature change, then it appears that it is explaining 94% of those changes. So almost all of the change in one variable would be explained by changes in the other variable. That's how strong this correlation is. So there you have it. This one is a nice and easy lesson. Hopefully you'll take your time and really think about our if and ifs statements. But if you have any questions, just let me know.